Hi everyone, this is our second video on exponential functions, and we're looking at transformations of exponential functions in this video. So specifically, we're looking at taking the basic exponential graph and looking at changing that basic function so that the graph is changed as well. This is not dissimilar to the kind of transformations we did with cubics and quadratics, where we looked at vertical translations, horizontal translations, and dilations and reflections. So similar sort of deal. Okay, before we go any further, let's have a look at the basic function again, just to remind you that we've got y equals a to the power of x here. I've just set a equal to 2 for the base. And as usual, the exponential graph cuts through the y-axis at 1, because when x equals 0, a to the power of 0 is equal to 1, and so that's why we cut through at 1. It increases quickly past 1 up to infinity, and below 1 to the left of the graph we can see that the graph decreases quickly towards 0 but never reaching 0. Remember that as x approaches infinity, the value for y gets smaller and smaller, but there is no value for x, so for which we would get y equal to 0 or y being negative. Okay, so just keep that in mind. Alrighty, so there is the basic graph. Now the first transformation we're going to have a look at is, we've done the basic form, so let's have a look at a scale factor, or otherwise known as, so I'll just go to draw mode, otherwise known as reflection and dilation. So the value of k will affect the graph in what way? What do you think having k as a large number will do to the function? Will it change the y-intercept? Will it change the x-intercept? What about k being negative? How will that change the function? What about k being a fraction? How will that change it? So have to think about that. And while you're having a think, I'll go back to Desmos here. And what I'll do is I'll activate the y equals k, a to the power of x function here. It's blue. Beautifully replacing the, or it's not really replacing, it's covering the basic function, because of course when k equals 1, we've just got y equals a to the power of x. Alright, so what happens when I make k bigger? I wonder if this is what you're thinking will happen. So when we make k bigger, we effectively make the y values increase by that amount each time. Okay, that's what it's being scaled up way. So it's actually increasing faster, not amazingly faster, because at the end of the day, the power is going to determine how fast this graph increases. So when x is a million, 3.5 times whatever that is not massively bigger kind of thing. But it does make a difference, and I guess it's worth looking at the y-intercept. You can see here that when in the basic graph we've got the y-intercept being 1, but in the scaled graph we've got k equaling, the y-intercept being 3.5. Go to a whole number so you can see that a bit more clearly. There we go. So k equals 4, and the y-intercept is equal to 4, unsurprisingly, because the basic graph is simply just multiplied by 4. Every value is. So the y-intercept goes from 1 to 1 times 4. 4. Okay, what about k being a fraction? I wonder what's going to happen. So as we go down, it's getting closer and closer to the basic graph. And then, well, not much really. It's just flattening out a bit, right? So there's k equal to 0.4, just under 0.5. And again, the y-intercept is now 0.4. If I click a button there, I should be able to see that. If I hover my mouse, there we go, 0, 0.4. So that's not surprising. I hope it isn't anyway. And again, the graph is slightly flattened out because it just can't race up as fast as it used to now that there's a fraction in front of it. It still goes down towards 0, as you can see on this left-hand side here, so there's not much difference. Okay, so the main thing when graphing or sketching this graph is that you have to change the y-intercept. what happens if we make k negative? The y-intercept's going to change, right? Getting closer to 0. And then, oh, there we go. Let's go to negative 3. There we go. So we can see, well, let's go to negative 1 first, actually, because then it will look a little bit prettier, I reckon. There we go. So as you can see, when k equals negative 1, that means we're looking at the function y equals negative a to the power of x. Now, note, when I write, so this is a reflected graph, right? So when I write y equals negative, let's just refresh that screen, try and get that to catch up with me. There we go. So when I write y equals negative a to the power of x, do note that that means negative a to the power of x. BODMAS says we need to do powers before we do multiplications, divisions, additions, subtractions. So you're literally raising a to the power of x and then making the result negative. It is not negative a to the power of x. That's entirely different. Okay, so it is not that. So as you see, as you can see, I hope that when we make k negative, we get a reflection on the graph. Okay, so all the y values that were positive become negative. 1 becomes negative 1. These values here are reflected down here. These values here are reflected down there. Okay, and then of course, if I make k a big negative value, it's just making it steeper. Or if I make it a negative fraction, it's just making it flatter. But it's still all the values are down in these two quadrants here instead. Okay, so that is k. That is what k does. It's a scale factor, or it does reflection and dilation if you prefer to use that language. Alrighty, moving on. This is a translation. Y equals a to the power of x, and then I'm adding t to the result. Is it a vertical translation, or is it a horizontal translation? Which one do you think it is? Give you a second to think about it. And okay, back to Desmos. I'll turn off that one. So there's my basic graph, and I shall turn on this one. At the moment, I've got t equal to 0, which means that the graph hasn't been transformed at all. It's the same as the basic graph. But now let's see what happens when I increase t, like so. There we go. The entire graph remains exactly the same, but gets translated vertically by that number of units. So when t equals 2, all of my graph is translated by 2 units. Effectively, I've gone from 1 to 3, 2 more units up for my y-intercept. Did you notice, I hope, that this blue line also followed? Okay, so this blue line is the horizontal asymptote. And the horizontal asymptote also moves. Remember how in the basic graph we said that when x is negative, y approaches 0 but never hits it? And that's called an asymptote, right? It approaches 0. Well, now, because I've translated 2 units up, the horizontal asymptote is now here at y equals 2. So that's the new asymptote, the value which the graph never goes underneath. Okay, so what does that mean? It affects what? Your range? Or does it affect your domain? Let you think about that. Which one does it affect? Okay, I'll let you answer that in a moment, but see if you got it right or not. So we can fill this in now. Is it horizontal or vertical? It's a vertical translation. Okay, so if this was the original graph, then a vertical translation increases it by a value of t. Now, what didn't I do? I didn't do negative. What do you think negative is going to do? The same, right? It'll just go underneath the basic. So that's obvious, I hope. But what might not be obvious is that although the y-intercept is pretty clear in that when I have t equal to negative 2, I've gone down 2 units, so my new y-intercept is negative 1. That's no drama. But because I've pushed my graph down underneath the x-axis so that the horizontal asymptote is below the x-axis, it means that we also have a x-intercept as well. Now, where I've got it here is pretty easy. It's equal to 1, but I could choose a value. So let's go to x equal to -4, t equal to -4, sorry. So that, even that's pretty easy. Let me go to -3 instead. So it could be that the horizontal asymptote, sorry, beg your pardon, wrong thing. It could be that the x-intercept is something quite different. In this case, it's 1.585, so it's quite a different value. So just keep that in mind, that the when you translate downwards, you get an x-intercept, and you have to use some techniques in order to work out what that x-intercept is. Y-intercept, easy. X-intercept, a little bit more difficult. You've got the skills to do it. I wonder if you can figure out how you do it, but I'll leave that for another video. Okay, let's spin on. Guess what this one is then? It's a horizontal translation. So when I graph this one, let me see, I'll turn that one off. Actually, I better just slide it back. So I'll turn that one off, and I will turn on this translation here. Now again, I've set b equal to 0. So when b equals 0, we've got exactly the same graph. I'm taking b away from x. But when I increase b, what's going to happen to the graph? I'm taking away b. So when I increase b, the graph effectively is sliding over to the right. It just looks like it's bending down, but that's not quite what's happening. It's actually translating to the right. So as usual with our translations, it's kind of the opposite sign. So because I'm taking away b, it's actually going across ways. So I'll just make it a whole number here. And I don't know whether you can see this or not, but there's the basic function at y-intercept, 1. So if I go down over to here and then down, you can see that it is now at 2, so 2 units across. So although it did look like it was just stretching out, it wasn't. It was actually, the whole graph was shifting over. And that kind of makes sense because now y equals 1 when x equals 2. 2 minus 2 is 0. So I hope that makes sense to you. So the translation is happening to the right. So as usual, look at the value of x minus b and say, well, I have to go sort of the opposite sign to what it says in here. If it said x plus 2, then it would mean I'd be going 2 units to the left. So I'll do that now. So again, it looks like it's just increasing faster, but it's not quite. It really is just translating. So 2 units across gets me down to -2. Okay, so there's y equals 1. Where is it happening? At x equals -2. Okay, so it's a translated graph. Maybe if I zoom out, you might see that it is actually the same graph, but just translated across a bit. There we go. So same graph, just translated across. Okay, so that's that's horizontal translations. Okay, so just remember, if you've got x plus something, it translates left. If you've got x minus something, it translates right. Like so. Okay, so if you keep that in mind, you'll be all right. So if we put all those things together, it would look a bit like that. You can do quite a few different kind of styles of functions. So y equals k a x to the power of, a to the power of x minus b plus d. So an example of that would be y equals 3 times 2 to the power of x minus 7 plus 11 would be an example of that. So that would look like, let's get those values. It would be, was it 3 times, so k is equal to 3, t is equal to, I'll make it 10 because I can't quite do 11, t equals 10, and b equals, I can only go as far as 5 as well. I'll make it 7, hang on, just so we can go as far as 7. I'll make this 11. There we go. So what would that look like? There's our basic graph. I'll just zoom in, like so, and just shift that over a bit. And our translated graph would look like that, with the horizontal asymptote being there. Okay, so we've gone up 10 units. Okay, from 1. Well, sorry, I should say we've gone across. We've gone across some units. We've gone up some units, and we've dilated it by 3 as well, which throws it all out. So putting all those in together means that our graph has been stretched out. That's the 3 times, and it's been moved across and up, as you can see. So it's a similar looking graph, it really is. It's still going towards 0 on this side and still going towards infinity on this side. It's just that it's been translated across, transformed. So that's basically it. So if you come across a function, you can sort of use your understanding of what this does and what this does and what this does in order to sketch it without having to do too much trouble. The only things you'll have to spend some time on is learning how to work out the x and y intercept when it's not clear. We'll do that in another video. Thanks, guys.